Hello, seniors. I hope you're doing fine today. Today, we're going to start with the last topic for the IB program, which is calculus. We're going to start with some basic concepts that you need to understand in order to be able to later on apply and correctly interpret derivatives and integrals, okay, which are for me, the most interesting topics of this program. So today we're going to begin with limits and convergence. We're going to be talking about different applications of calculus into real life situations later on during live sessions, but there are lots and lots of real life applications for this concepts that you're going to be learning now. Okay, so let's start with this first topic, which is limits and convergence. The objectives for this class are two. First of all, define and understand the concept of limit and convergence. And number two, apply limit notation. Okay, so let's start by defining what convergent sequences is. This is a concept that we've seen already in algebra. It says, convergent sequences is a sequence in which, as the term number of the sequence increases, the terms in the sequence approach a fixed value known as the limit L of the sequence. So this is like, we've seen this in algebra when we talked about sums to infinity, right? Those were examples of convergent series or convergent sequences, right? So it's the same concept. And okay, so this is a limit notation. We're going to be applying this into different problems later on, so don't worry if you don't understand this right now. It basically is the limit of a function when x tends to a specific value c is the limit of the function, okay? It's denoted as L, as capital L, right? So this is read as the limit of the function f of x when x tends to c, and it's L, okay? That's the value of the limit. Obviously, this is a number, this is a number, and this is a function, right? So we're going to be seeing that into concrete examples later on. Okay, so let's see an example in order to try to start understanding how to apply this limit notation. It says, Jose decides to walk in a very particular way. Each step he makes is half of the previous step. He starts his walk with a 1 meter step. How far can he get? Okay, so this is an example that we have seen already in the sums to infinity sequences, right? So you'll see that the same concept apply here. So for the first step, if I'm going to be finding all of the different sums of my steps because I want to know how much I walked in total, right? So I'm going to be finding the S, which is the sum of the different terms of a geometric sequence in this case. Okay, so if I start with 1 meter, then S1 would be 1. I walked 1 meter in total. I'm going to write 1 meter. Then S2, if I walk 1 meter as the first step, I'm going to walk half of it for the second step, that is 0.5. So the second step is the total steps or the total distance covered is right now 1.5 meters, okay? Then I'm going to find S3, which would be the previous sum plus half of 0.5, which is 0.25. This would be 1.75 meters. And so on. I'm going to be doing that for at least 6 steps here. So this is 1.75 plus 0.125, right? If we add this is 1.875 meters. Then if I add 1.875 plus half of 0.125, that's 0.0625. And this addition is 1.9375. You may do this in your calculators to follow if you want. Finally, if we do one more, this would be 1.9375 plus, this should be 0.03125. If we add this is 1.96875 meters. So do you notice a pattern here when I am adding the values. You see that, first of all, the difference looks quite big, right? But as I keep on moving, you see that the difference is converging, or the addition is converging to a value, right? The difference between this term and this term is actually small, right? So we're converging to a value, which would be, if we keep on doing this, we'll be adding 1 point, or we would be getting actually 1.99999 and so on meters, right? So this converges, we could write this as 1.9, and this keeps on going up to infinity. So it's converging to 2, right? So we would, if we use limit notation to express this, we would say that the limit of our function, which is in this case the sum of all of the terms, when n tends to infinity, that is when I keep on increasing this up to infinity, is equal to 2, right? If I keep on adding, the maximum value I would get is 2, right? And if you remember that from the sum of infinite terms of an infinite geometric sequence, we could find that by using this formula, right? U1 in this case would be the same as S1, which is 1, divided by 1 minus R, where R is a half, right? We're doing half of the step each step, half of the previous step. Okay, so this is 2, right? So we get the same value, or actually they are the same value. The limit and this value over here represent the same thing. So this is what limit notation is about, okay? Then we have the opposite definition. We've seen convergent sequences. Now we're going to see divergent sequences. And you see that it's exactly the opposite, right? Divergent sequences are sequences that are not convergent. This is as the term number increases, as the term number of a sequence increases, the terms in the sequence do not approach a fixed value. That is, they keep on growing indefinitely, right? They do not approach a specific value like in the example we've seen recently. So let's see this example in order to clarify this. It says, determine whether each sequence is convergent or divergent. If the sequence is convergent, give the limit of the sequence. Okay, so part A. The sequence is 0.3, 0.33, 0.333, 0.33333, and so on. So this sequence is convergent, right? We're converging to a value. If we keep on doing this, we would reach to 0.3, and the small hat that indicates that this keeps on increasing, the 3's. And if you realize, this is the same as saying 1/3, right? So we're converging to 1/3. That's our converging value. So we would say that this is convergent, right? Convergent. And we would say, if we use the limit notation, we would say that the limit of the function, I'm going to call it un, when n tends to infinity, is 1/3. That's the value of that's the converging value, right? Which is the same as saying 0.3 and the small hat over there, right? Like that. Okay, so that's A. Then we have B. What do you think about B? 2, 4, 8, 16. We see that the terms are increasing, right? If we keep on doing this, this would be then 32, then we have 64, then 128, and so on. So we're not converging to a specific value. This keeps on increasing until infinity, right? So in this case, we're talking about a divergent sequence, right? So I'm going to write divergent. And since it is a divergent sequence, it does not have a limit, right? So does not have a limit. And that's it for part B. Then we have part C. We have these fractions over here, 1/5, 6/25, and so on. Maybe if we write this as decimals, we could visualize what's happening better, okay? So I'm gonna write 1/5 as a decimal, that's 0.2. 6/25 as a decimal, that's 0.28. You can do this in your calculator if you want. 31/125, that's 0.248. Then 0.2496. And finally, the last term is 0.24992. So now, by looking at these terms, and this keeps on, by looking at these terms, are we converging to a specific value? If you look closely, you'll see that we are converging to 0.25, right? The values are slowly increasing until they reach, this will keep on being 0.249999 and so on, until we reach the converging value, which is 0.25. Okay, so we're gonna say that this sequence is convergent. And that the limit of this function, I'm going to call it un once again, when n tends to infinity, is equal to 0.25, right? This is our converging value or limit, which is the same as saying, if you want to write it as a fraction, 1/4, okay? Finally, we have part D, which is, we have 1, -1, 1, -1, 1, -1, 1, -1, and so on, okay? So the question is, are we converging to a specific value here? No, the answer is no. We're not converging to a specific value here. We're just switching between 1 and -1, 1 and -1, but we're not approaching a specific value like in part A or part C, right? So case D is also divergent. So let me copy that. Divergent, and it does not have a limit. Whenever we talk about divergent, it will never have a limit, okay? So if you identify a divergent sequence, you already know that it does not have a limit. Okay, then we have this part. It says limits of functions. The limit of a function when x tends to a value c is L means that as the value of x becomes sufficiently close to c from either side, that's when we come from the left and when we come from the right side, I'm going to explain that in an example later on, the function f of x becomes close to a fixed value L. If the function does not become close to a fixed value L, we say that the limit does not exist. Okay. We're going to see all of this concept in some examples later on. Okay, this is something very important. There are 3 ways in which we can determine the limit of a function. The first one is by doing it graphically. Then we have another method with it, which is numerically, and I added a third way, which is algebraically. Okay, we're going to see the 3 ways to find the limit of a function. It says you can use a GDC to help find the limit of a function. If you do it graphically, you can graph the function and examine the values of f of x when x is near c. Numerically, you can make a table of values and examine the values of f of x when x is near c. And the third way, it says the limit of a function can also be found algebraically, I think that's correctly written, by factoring the algebraic expression and eliminating terms that cause indeterminations. Okay, so we're going to see all of these 3 ways of finding the limit of a function in the following examples. Okay, another concept, it says continuity and discontinuity of a function. Continuity, the definition of continuity is a function is continuous of f of at x equals a if, and we have 3 conditions here. If f of a exists, that is, when I replace the value a given into the function, I can actually find a value, it exists, right? Then if the limit of the function when x tends to the same value a exists, so both the limit and the value of the function should exist. And the third condition is that both the value of the function when x equals a should be equal to the limit of the function when x tends to a. I know this may sound confusing, but just wait until we get to the examples and you will understand this better. Okay. So the three conditions must be met for the function to be continuous at x equals a. If one of the above conditions is not met, the function is discontinuous at x equals a. Basically, continuous means that the function, if I draw it like this, for example, the function, whatever function this is continuous, or it does not have any jump throughout the graph, right? And discontinuous is when we have a jump. For example, we have a function coming here, and then boom, it jumps down here and continues, right? That's the difference between continuous and discontinuous if you want to put it into graphical ways, right? Okay. One last thing before we get into the examples. These are some things you need to remember. Whenever you see 0 over 0, this is called an indetermination. There's no actual solution for this. The only thing we can do is try to solve for the indetermination, which is done by applying factoring cases, right? Which we're going to see again in the examples later on. But if you try putting this in your calculator, you should get math error, and there's no actual value for 0 divided by 0. Now, for this case, whenever we have n divided by 0, where n is any value, right? 1, 2, negative 10, whatever, any number divided by 0 is either positive or negative infinity. It would be positive infinity if n is greater than 0, or if n is positive as well. And it will be negative infinity if n is also a negative value, right? Negative 10 divided by 0 is negative infinity, and positive 10 divided by 0 is positive infinity, okay? Finally, property C says that 0 divided by any number, it's always 0, right? 0 divided by 1 is 0, 0 divided by 10 is 0, 0 divided by negative 8 is 0, and so on, okay? Any 0 divided by any number is always 0. Okay, and this is very important for you to remember. N divided by 0 is not an indetermination as in this case. N divided by 0 is actually a positive infinity or negative infinity. So it's like, it's kind of a number, right? It has a solution. If you plug in this into a calculator, you will also get math error, but it's because the result is infinity, which is a mathematical concept and not actually a number, okay? So now, let's see the examples to try to finish understanding what the concepts of limits are, okay? So it says, use a GDC to examine each function graphically and numerically, and I added and algebraically. We're going to study the function in the three ways mentioned before. Find the limit or state that it does not exist. And I also added here, determine the continuity of the function for the given value of x. So we need to examine the function in the three ways mentioned before. We need to state the limit or state if it does not exist. And finally, determine the continuity, if it's continuous or discontinuous at the given value of x. Okay? So let's start with a simple exercise. It says determine the limit of this function, which is x squared, when x tends to the value 2. Okay, so let's start with the first method, which is graphically, okay? What we're going to do is we're going to graph this function, f of x equals x squared. You can do that in your calculators, and you should get a parabola, right? So this, let me write that here. This is f of x equals x squared, right? We're graphing this interior function over here. So we get the graph of a parabola, right? Now we need to analyze what's happening when x is 2, okay? When we are approaching 2 actually, right? So what I'm gonna do is I'm gonna identify x equals 2, and I'm gonna trace the line to see where it intersects the graph, right? So, I'm gonna do it like this. You see that for x equals 2, the graph is actually at y equals 4, right? So I'm gonna mark this point over here. So, when we are analyzing the limit of a function, we don't care about the value, this specific value that the function is taking, which in this case is y equals 4. We don't care about that value, but what we do care about is to what value or values, depending on the case, the function is approaching when we're approaching x equals 2. So here is where we're going to analyze from a limit perspective. And since we want to find the limit when x approaches 2, we're going to, first of all, approach from the left to 2. So we're going to approach from left to right to the value 2. And you will see that if we follow this parabola over here, when we're approaching to 2, we're from the left side, we are approaching it like this, right? And if we do the same for the right side, so we approach 2 from the right side, that's from right to left, you would see that there, you would see that kind of, if we approach from the right, we are actually approaching to the same value, which in this case is this value over here, right? So once again, we do not find this value directly by plugging in 2 here and it's 2 squared equals 4 and that's it. But we need to, when we're analyzing limits, we need to analyze where we are approaching when getting to x equals 2, right? Where the function is approaching when we're approaching to x equals 2. I know it's a kind of confusing concept, but that's how it works, okay? So we're going to write, now that we have identified that we're approaching to the same value from both sides, then we can confirm that the limit of the function, which is x squared, when we're approaching the value of x equals 2, is 4, right? Because we're approaching to the same value from the left and from the right, okay? That's why we can conclude that the limit is 4. And we also know, remember the two conditions to determine if the function is continuous, 3 conditions, sorry. We already know that the limit exists and the value of the limit in this case is 4. We also need to determine this, if f of a exists. So we need to calculate f of 2 in this case, that's our value of a. So f of 2 is 2 squared in this case, and this equals 4. So you see that this value and this value are the same, right? So we're fulfilling the third condition, which is that f of a should be equal to the limit of f of x when x equals a, or tends to a, sorry. So because of this, we're going to say that f of 2 is the same as the limit of x squared when x tends to 2, okay? So because of this, we can conclude that the function is continuous, continuous for x equals 2, okay? So this would be the second part of the answer, and the first part is find the limit, okay? And we found the limit here, which is 4. Okay. I think that, well, we still need to do this numerically and algebraically, but I think that this will be more clear when we get to this second exercise, and you'll see why. Okay, so we determine the limit of the function graphically, and we also determine its continuity, right? You could also determine the continuity just by observing the graph. If there's no jump here, then the function is continuous, okay? That's how you quickly identify if it's continuous or not. Then we have the second method, which is numerically. To do this numerically, what you need to do is build a table. So I'm going to write the function here, f of x equals x squared. And I'm going to do a table with the x and f of x values of this function. So it's basically x and y, right? So what I'm going to do is, I'm going to do this quite long. I'm going to use values of x. If I want to find the limit when x tends to 2, I'm going to pick values which are very close to 2 in order to see what's happening with the values of y. Okay? So, for example, I could pick 1.8. I'll be approaching 2 from the left first. 1.8. And then we could also pick 1.9. Then we can also pick 1.99 and so on, okay? Maybe 1.999 in order to approach 2 as close as possible. I'm going to write 2, but we're not going to be using this value. And then I need to approach from the right. So other values would be 2.001 or maybe 2.01 and so on, okay? You could give more values, but I think that with this we're fine. Okay. So I need to evaluate this function for all of these values of x. In order to not waste time, you could do this in menu table in your calculators instead of doing it by hand. So if you do that in your calculator, you should be getting these values. For 1.8, this is 3.24. For 1.9, this is 3.61. For 1.99, it's 3.9601. And then we have 3.996001. For 2, this would be 4, right? 2 squared is 4. For 2.001, that's 4.004. And finally, for 2.01, that's 4.0401. Okay, so because we're analyzing the limit and not the actual value for x equals 2, I'm going to discard this. I'm not going to look at this, but rather I'm going to analyze what's happening when I'm approaching that value, which is x equals 2, right? So you see that when I'm approaching x equals 2 from the left, you see that the values are tending to what value of y? You see that we're getting closer and closer and closer to 4, right? From the left side. So we're also looking here to what value of y I'm approaching. So y tends to 4. And if I do the same analysis from the right, I'm going to say I'm coming from right to left in this case. I'm approaching 2, x equals 2, and I'm comparing the y values. And once again, we see that the y values are tending to 4. So once again, y tends to 4. And because this value is the same as this value, then we can conclude that the limit, let me write that here, the limit of x squared when x tends to 2 is equal to 4. Okay? You'll see that in some cases, whenever we approach from the left, this is expressed this way. The limit of x squared when x tends to 2, and you'll see a negative sign here on top. It's like to the power of negative, right? That means that we're approaching from the left, and this equals 4, right? We got this here. And if we do the same from the right, it would be the limit of x squared when x tends to 2, and we're going to write a positive here. That means that we're approaching from the right, and this equals 4. And because this value is the same as this value, then we can conclude that the limit of the function is actually that value, okay? So I'm showing you this because you're going to be seeing this in some examples as well. So this is how you do it numerically. You build a table and you see, and you compare to what values of y the function is approaching to. Finally, we have the third method, which is algebraically, which is just trying to replace the value of x with the value that we're given. In this case, the x is approaching to 2. Okay, so it's basically like this. We're going to write the limit of x squared when x approaches 2 is equal to, and we just replace this value 2 into this function, and we see what value we obtain. So this is 2 squared, and this equals 4. Okay? Now, in some cases, this method does not work, or actually it works, but we need to do something else, and that's what I wrote here. Observation: if there is an indetermination, solve the indetermination by applying a factoring case. We're going to see this in the following example. Okay, so that's it for the first example. We determine the limit of the function, and we also determine its continuity, right? We found that it is continuous for x equals 2, which is the given value for this exercise, okay? Okay, so now let's go to part B, to exercise B, and I think you're gonna get this concept a little bit clearer now in this example. So I'm gonna write this down here. I think it's already written, yes. So we want to find the limit of this function, x squared minus 1 over x minus 1, when x approaches the value 1. Okay, so we're gonna do the same three methods. We're gonna start by graphing this. If you graph this function into your calculator, you should see a straight line. Okay, that's the graph of this function. And in some cases, in some calculators, you will see that there's a small gap in here. Okay, there's a small, well, discontinuity point there. Why? Because if you try replacing, you see that it occurs at x equals 1. If you try replacing the x value with 1, you will get 1 squared minus 1 divided by 1 minus 1, and this is a famous 0 over 0 case, which is an indetermination, right? That's why we're getting this small gap in here, okay? So let's see what happens to the concept of limit and the value of the function in this case. And we're going to analyze if the function is continuous or discontinuous or not. Okay, so if we analyze the limit graphically, we're going to be doing exactly the same thing we did in the previous exercise. We want to find the limit when x approaches the value 1. So we're going to identify 1 and see where it is. Let me do it with a different color. If I approach 1, you see that we have this value of y over here, which we don't care about because when we're analyzing limit, we're actually analyzing where we are approaching to. So if I approach the value 1 from the left, I'm going to be following the function, and you'll see that I'm going to be approaching this value over here, right? Let me draw. This is a discontinuity point, right? It is not defined, so I'm going to do this. I'm going to paint this with a not colored circle or not filled circle, right? That's how we represent a discontinuity point. And if we do the same thing from the right, if we approach the value of x, we approach here from the left. Now we're going to approach it from the right. You'll see that you'll see that we are going to be approaching to the same value, right? If I approach this from this side, I'm going to be getting, or I'm approaching actually to the same value, which is this one over here. Okay, so the limit actually does exist, and the limit is 2, right? So I'm going to write that here. We're going to say that the limit of this function, which is x squared minus 1 divided by x minus 1 when x tends to 1 is actually 2, right? We're approaching to the same value from the left and from the right, okay? But if we analyze the value of the function for x equals 1, you will see the following. So f of 1, which is the value of the function when x equals 1, is 1 squared minus 1 divided by 1 minus 1, and this gives us 0 over 0, which is an indetermination. There. So you see that in this case, the value of the limit is not the same as the value of the function. So we're going to write it as f of 1 is different from the limit of x squared minus 1 over x minus 1 when x approaches 1. And as they are different, we're going to conclude that the function is discontinuous for x equals 1, right? Because the third condition, which is that this should be the same as this, is not fulfilled, right? So I hope this concept of limit is a little bit clearer now through this example. So we found the limit, which is 2, and we determined that the function is discontinuous for x equals 1. Okay, so that's for the graphical method. Now, if we go to the numerical method, if we determine the limit numerically, we're going to do exactly the same thing. We're going to build a table where I'm going to write x and y values, or f of x, however you want. And I'm going to pick values that are very close to 1 in this case, right? Because I want to determine what's happening when I am approaching 1. So I'm going to pick the values 0.9, and then we could say 0.99, then we could say 0.999, and so on. You can keep on writing values if you want, but I'm going to write it up to there. Then we're going to analyze what happens at 1, and then we're going to approach from the right. So we're going to say 1.001, 0.001. Another value could be 0.01, and another value could be 1.1, right? Okay, so if I find the respective values of y, you can do this at menu table using your calculators. Just replace the value of x into the function, and you will be getting the different values. So for 0.9, it's 1.9. For 0.99 is 1.99. Then we have 1.999. For 1, if you do it in your calculator, you should get the indetermination, so you get an error in your calculator. So I'm going to write error. Then for 1.001, this is 2.001. Then we have 2.01. And finally, 2.1. Okay, so once we have this table done, we're going to follow the same concept. We're gonna approach the value x from the right side, from the left side first, here. So you see that as we're approaching the value 1 from the left, you see that the values of y are approaching to 2, right? They are converging to the value 2, right? So y tends to 2, we're going to say. And if we do the same analysis from the right side, when we approach the x equals 1 from the right side, you see that the y values are also converging to the value 2. Y tends to 2. And this is not always the case, right? There are some cases in which when we approach from the left, the value we get is not the same as when we approach the function from the right. You will be seeing that in the last example. Okay, so as these two are the same, I can write this once again as the limit of x squared minus 1 over x minus 1 when x approaches 2 from the, when x approaches 1 from the left, and the limit equals 2, and the limit of x squared minus 1 over x minus 1 when x approaches 1 from the right is also 2. So as both are the same, then we can conclude that the limit of the function x squared minus 1 over x minus 1 when x tends to 1 is equal to 2. Okay? There is no need to write this and this. I'm just showing you this for you to understand this better. Okay? So that's how we determine the limit numerically. And finally, algebraically, which I think is the shortest way, is to do the following. We're going to write the limit when x tends to 1 of x squared minus 1 over x minus 1. And the first thing we're always going to do is we're going to try by replacing the value of x, the given value of x, in this case it's 1, into the function and see what happens. So this is 1 squared minus 1 over 1 minus 1. This gives us 0 over 0. So this is an indetermination. But we're not getting the same values as we got here and here. So there's something that we need to do in order to get that value. And here is when we're going to apply this observation over here. It says, if there is an indetermination, solve the indetermination by applying a factoring case. Okay, so we need to solve this indetermination by applying a factoring case. And if you take a look at this function over here, what factoring case can I apply here? Specifically on the numerator. I can apply difference of two squares, right? So by applying factoring cases, I would say that the function is x minus 1 times x plus 1, right? I'm applying difference of two squares on top. And for the denominator, I cannot do anything here, so I'm going to write x minus 1. And you see that here, I can eliminate this term x minus 1. And that is the term, whatever term we eliminate is the term that is causing the indetermination, right? So now what I'm going to do is, this obviously equal to x plus 1. Now I'm going to replace once again the value of x with the given value of x of the exercise, which is 1, right? And you see that 1 plus 1 is 2. And that's exactly the value of the limit of this function, okay? So finally we would write this as limit of x squared minus 1 over x minus 1 when x approaches 1 is equal to 2, this value we got over here. Okay, that's how you find the limit of a function algebraically. Okay, I want to see one last exercise, but we're only going to be doing the graphic method for this one, just for you to finish understanding the concept of limits. It says, find the limit of f of x when x approaches 0, and the function f of x is given this way. This is known as a piecewise functions, right? I remember I told you that already. This is a función a trozos. And it's 1 for x greater or equal than 0, that's when x is positive, and the function is -1 for x less than 0, or for when x is negative, okay? So whenever we have a function which is y equals 3 or y equals whatever, remember this is an equation of a horizontal line, okay? So the piecewise function that we're given in this exercise, if we do a quick sketch of this function, we should get something like this. This is x, this is y. So it's equal to 1. I'm going to put 1 over here and -1 over here. I'm going to put this a little bit down. -1 and 1 is, oh, 1 is fine there. Okay, so the function is 1 when x is positive, right? Greater than 0. So greater than 0 means all of the values from here to the right. And it's equal to -1 when x is when x takes negative values, right? So that would be a horizontal line from -1 towards infinity, right? So this is how the function looks like. It comes from the -infinity up to this value, and then it jumps to to 0 and to 1, and then it goes, and it keeps on being 1 until positive infinity. You see that the equal sign is included in this function over here, in this one, okay? So for x equals 0, we're going to be using this value here, and this one should be a unfilled circle, right? Because the function is not defined here, as we do not have the equal sign down there, okay? So this is how the function looks like. Horizontal line at y equals -1 before x is 0, and horizontal line at y equals 1 after x is 0, and it also includes 0. Okay, so now that we have the graph, we're gonna analyze the concept of the limit, okay? So whenever we're doing this graphically, remember, we want to know the limit when x tends to 0, okay? We're looking at x equals 0, which is here, okay? So for that value of x, what's happening with the limit? And if we approach this, or if we analyze this from the left, we're gonna approach to, when we're approaching to x equals 0, you see that we're approaching to this value over here, and we're approaching x equals 0 from the right, from right to left, we're approaching this value over here, right? So you see that we're approaching different values here. So I'm going to write y tends to 1 here, and y tends to -1 in this case. So as they're approaching different values, we're going to say that the limit, or before writing that, just to make this clear, I'm going to write this, that the limit of f of x of the function when x approaches 0 from the left is -1, and the limit of the function when x approaches 0 from the right is +1. So since these two are different, we're going to conclude that the limit of f of x when x approaches 0 does not exist, right? We're approaching different values. But the value of f of 0 does exist. The value of f of 0 is this value over here, which is 1, because it is defined for x equals 0 in this category, okay? So the function is defined, but the limit does not exist. And since since both of these values are not the same, we conclude that, so as f of 0 is different from the limit of f of x when x approaches 0, we're going to conclude that the function is discontinuous, once again, discontinuous for x equals 0. Okay, so it is discontinuous, and in this particular case the limit does not exist. So we have covered all of the three different alternatives. When we have continuous functions where both the limit and the value of the function exist and they are the same, we have seen discontinuous functions where the limit exists but the function is not defined for that specific value of x. So that's one type of discontinuity. And the second type of discontinuity is when the limit does not exist but the value of the function exists. So we have a discontinuity. Okay, so I hope this was clear enough for you, seniors. You're going to be doing some exercises to practice with this, and please let me know if you have any doubts about this. Thank you for your attention. See you.